to get as a learning objective is to understand the concept of shape efficiency. Yeah, so here we're talking about the shape, not to a great extent, but let's say to a limited kind of domain that you can manipulate. But even though you can still find many useful or great improvement when you just consider the shape efficiently. So we'll go to the definition and so on later on. And with that, you would get the kind of ability or skill to do your design, not just based material selection, but you can also have a combination of material and shape selection. That will be demonstrated later on by example. In the end, so we would like to make you aware how the material and the shape could interact, and in the end to allow you to do the design with both of them. So the resources for this concept and also some examples are in the book you have read already. Let's move to the next slide. Yes, so this is our usual slide. So we will start now. We will start a group discussion in about, so here's 10, actually it's in about 15 to 20 minutes. And then you have 30 minutes to discuss and even another 10 for a small break. So we'll be back in 1 hour and start our group presentation at 9:15. So the outline for today's, let's say the review lecture, is simply covering 4 topics. First of all, I would like to give you the definition about shape efficiency, and it's related to a few shapes that you could play with. The second one is how the shape factor is calculated and what is the kind of upper limit of the shape factor. The last 2 points actually is given via one case study or one example. So how would you use the shape factor together with what we learned about the material index to do the selection of shape and the material at the same time, and even express it via the graph software. All right, so what is the shape efficiency? So shape, you know, that's what it is. But we have to, as I said, we have to be a little bit limited here because we don't want to explore too much about the shape or too general. So we're usually fixing ourselves into a cross section. So we don't want to go to the entire shape of a structure. I will show you what that means in a minute. In that sense, we have a few options like tubes, I-beams, and the hollow box section, sandwich panel, and so on. Then what is efficiency? So let's say the efficiency is basically to use the shape, the freedom to choose the shape to save our material. So basically for a given stiffness or strength, a given mechanical requirement, and we can fulfill that with the least material. With the least material, meaning you would try to explore the shape that can help us to get the required stiffness or strength. That will be also more clearly explained in the next slide. So what we have to keep in mind is that the shape is something related to the material and the processes. So for the processes, you probably could understand, because we cannot shape anything as we wish. We have those typical, let's say, shape forming processes like rolling, extrusion, and so on. that will give us very often some regular shapes. Yeah, that is one limitation for the shape factor. The other one is actually the local buckling. That will be also explained later on. So first of all, we need to know the shape is usually, so when we design the shape, we don't design for a general purpose. So we have to design the shape according to the loading of the mode of the loading. This is important, well, not too important at this moment, but this will be pretty important for the task 5 actually, which has been released hopefully already. You would see. So when you have a certain loading, then you design your shape or you select your material accordingly. The loading that we're talking about mainly actually is either tensile, torsion, and sorry, this is bending, torsion, and compression. So these are the 4 very typical loading, and you could also have combinations of them. And you can see we always have one. So this is this case, this solid beam. This is our reference case, which will be explained later as well. So everything about the shape factor is defined based on this guy. Basically, when you have a square and it's a solid square as your cross section, and you would define all the kind of reference mechanical property based on that. And when you just change the different shapes, so here we have to be specific. We're not changing the entire shape. So you can see the assumption is basically we have a uniform kind of extrusion of the cross section. So we don't allow any kind of tailoring when you have different positions on the longitudinal direction, which is just to make us easier to understand the concept and to do the design. But actually, in a reality, you would say there are processes that are really tailoring the thickness somewhere and there to just make sure your loading is more efficient. But that's the topic we're not gonna cover today. You just need to know this can be a degree of freedom as well. So you can see the I-beam, which is known for resist bending. So it is very good for the bending stiffness. And of course, for these tubes, they're good for torsion and compression and as well. Actually, the compression for the I-beam is also not too bad. Good. So here is the kind of example how you calculate the shape factor. So first of all, the shape factor is a dimensionless factor, which is basically the mechanical property of a kind of shaped cross-section over our reference cross-section. So if you just jump here to say this shape factor, this is the elastic bending stiffness shape factor, or you can also simply call it the elastic shape factor, is, for example, the bending stiffness S over of this shaped profiles over the reference one, this guy here. So the bending stiffness basically can be related to the E modulo of your material and the second moment of the area, which is this I. So I think from the task 1, you learned how to do the calculation of this, either just by looking at the book, or you also did it like this with a very systematic mathematical derivation. Both will be okay, and the main message is for you to learn how you can get this second momentum of the area. They will differ a little bit, but not significantly. In the end, you will have this shape factor as a function of the second moment of your your shaped profile over the area of the reference one. So you can see for this function, basically it's a function that you with a given area that you have, you basically will get their final value. So that is the result of it. We don't show the details, but you can see the shape factor basically is 10. Meaning what? Meaning with the same area of this small square, or with this kind of a shaped I-beam or tube, you will have 10 times better property, or in terms of bending stiffness, with this I-beam or tube than our simple reference cross-section. That is a huge improvement. So it's like you're choosing carbon fiber over a soft material with nothing but just change the profile, change your design a little bit, or even not the whole design, only the cross section. So this is important for us to really consider when we do the design. I think this also explain to some of you, if you don't sense it, why in our daily life this kind of structure is always C, because it really has very good shape efficiency. Yeah. If you just convert it, when you reach the same amount of bending stiffness, this will save 90% of the mass. So basically, the cross-section area can be converted to mass if you have the same length of the structure. So that is a great optimization of your mass. All right, that was for the elasticity, and now let's move to the, let's say, the plasticity, which is about the bending strength. It can also be generalized to overall strength, because that will not differ too much. The same method is applied. So here we're talking about bending strength, this FF, and you know this can be correlated to the yield strength of your material, and also to this section modulus of the area, which is this Z. And after you do certain calculation, so this is simple for this square, and for the shaped area, it's a little bit more complicated. But you know how to do that from the book either. And this is the final equation. So here we don't have a explicit value of it. It will be dependent on the detailed shape that you choose. So now that's the kind of process how you get the shape factor calculated. And with this diagram, I'd like to show you what are the typical shape factors in terms of profile that we see in daily life, and also in terms of materials that we often use. Let me see if Professor Sven Boschut is here. Okay, it's not. Here we have one question for you that you could discuss during your group work later on. If you notice, there are two lines. So there are different shapes and different materials in combination. And first of all, you have this reference line, which is the shape factor as 1 right here, meaning you're having your material as what we called as reference stage. And then you could have the shape factor of 100 for some materials. But for most of them, it's something between 100. This is the kind of upper limits, this 100 of our material and also of our shape. There are two limiting factors. But I want to ask you, if you look at here for some extruded aluminum angle, actually this is already the truth, but you see there's some profile which is below than 1. Maybe you could think of what is reason. Can we have the kind of profile of material with the shape factor below 1, and what that could be? We will try to talk about that during the group presentation phase as well. Okay. Yeah, we said most of the shape factors are between 1 and 100. And so here is a list of some specific cases. For example, for steel, we usually have the elastic shape factor around 65, or the upper limit is 65. And plastic is often much lower, which is 13. So with this, we want to make you aware that there are two constraints about the shape factor. The first one is manufacturing. So we cannot manufacture any shape that we want with our conventional methods, at least. But if you are familiar with the engineering world, maybe one of the booming research areas now is related to 3D printing, so additive manufacturing. That is really breaking out our conventional, let's say, manufacturing methods significantly, because you basically don't need to design so many rollers or tools or whatever to do those conventional extrusion, rolling, and shaping, basically. You can really build up any shape as you wish with the additive manufacturing. So if we just actually include this manufacturing method, which is not used massively yet, but it is applied to certain components making, and this value will be significantly increased. Yeah, but we have to be aware that this is only concerned about the manufacturing constraint. Yeah, we have also the second limit, which is called this, related to the local buckling, especially when the structure is long, like a slender. Of course, if it's short, that this value will be not that significant, not that important anymore. But when we're talking about a long structure, we have to be aware that might be the risk to have local buckling. Is something you cannot really predict, because it's related to the geometrical defects on your surface. But there is a certain theoretical estimation about this risk of local buckling, which is given by this equation related to your E modular and also the yield strength. So basically, if we just take steel, you would say this value is around about 30, 40. So we cannot go even to the kind of empirical limit too much if we're designing a long kind of product. Once again, if it's a short, actually you can just break this value. Good. So that's the introduction about shape factor and their upper and lower, their upper limits. Here is one example that shows you how we can do the selection in combination of shape and material. So the example is quite simple. So now we have just a structure, or we want to design a structure that to have very good resistance over bending, even 3-point bending, let's say. We don't want to fix kind of the cross section here. So different from your previous tasks. So here we all in those ones, you always have kind of a constant shape which you cannot vary. You just choose the material. So here we don't want to change we don't want to fix our cross section. So over here you're free. You can do whatever design you want. But of course, the L is a fixed number, so you have a fixed length. But the area is is changeable. The objective is, of course, to minimize the math. Yeah, that's why if you just kind of minimize the area here, you will minimize the math automatically. But we need to get sufficient stiffness out of it. So how this is done? We first basically calculate the constraint, which is this bending stiffness, S. So you know the equation, which is related to the constant E modular, the second moment of area or cross section, and L. And then you just introduce the area out of into the equation, which is here. And if you remember the equation we just showed you before, you can also introduce the shape factor writing into the equation already. And of course, the mass is nothing but AL and the density. So if we now just try to bring the A out, we don't want to see A, we want to see all the rest, and replace A with the combination of these two equations, and you would get your shape factor in, you would get your L in, and you would also get the E and C. So this second moment is also replaced by this equation. So this is the final equation you see here. So we have the first component of it, which is completely constants that we don't need to change. And this second component basically is our design component. So you have rho and you have the shape factor, you have the E modular. So if we want to minimize the math, we basically want to minimize this whole component. So this is what I said. As before, if we just consider the constant shape, meaning we have a constant shape factor, you are very familiar with this equation already. You know so many different ways to find a very good material in terms of this. And actually, if you just look at this simple table here, you would say the wood is giving the best combination of rho and E modular. This is also, we have discussed it once actually. Some of you gave wood or bamboo as the best component in some cases. This is the reason of it, right? But if we just consider the shape factor into it, now you could see for the wood, we have a very low shape factor, which is 8. That is usually connected to the manufacturing process, as you know. With that considered, if you just look at the second term, so now we found out aluminum gives much better overall property. So this is actually part of the reason why for the exercise before we didn't, in reality, we didn't go for wood, although it gives the very good rho over E modular. All right, that's one way to do the kind of selection, but you know this is rather exhausting. Of course, the better way is to use our HB diagram, that you can have a very good graphic overview about the whole material library. And this is something you have been practicing, I guess, from our exercise as well. You have such a factor, and now we just bring the shape factor into it. You would have a rearranged rho and also E modular, and then you can put this into the diagram. If we just look at the shape factor as 1, you see aluminum is here, which is not one of the best. But when you just have the shape factor included, you right away bring aluminum to there. So you're pushing this selection line much forward. That gives us a benefit for the better shape, for the better choice of mass minimization. All right, I think that's all I would like to review from what we have learned and that will give you a starting point also for our discussion later on. So here is basically a simple summary of what I talked about. So when we just bring the shape factor into account, you're not just simply considering this material index, but you're rather consider a shape related